So for the second example, we'll do a surface integral. So your book does the same integral with a different parameterization. You're going to get the same thing no matter what parameterization you use, but we'll do a different one. So sigma 2 is going to be the top half of the unit sphere. So this is, the regular sphere. We're just considering its top half. And we're going to parameterize it by phi theta maps to sine phi times cosine theta, sine phi times sine theta, and then cosine phi. There's a typo in your book. It should be cosine phi, not cosine theta. And phi inverse of sigma 2 is the rectangle in phi theta coordinates, this rectangle. And you don't have to take my word for it. You can check this for yourself. So like, if you plug in phi equals 0, for example, you'll get the point 0, 0, 1. If you plug in phi equals pi over 2, you'll get the unit circle in the R2 plane, or sorry, the XY plane, etc. And you can use sort of surfaces of rotation sort of theory to get the rest. And what we want to integrate is integrate over sigma 2, the 2 form alpha, which is 1 over x dy wedge dz minus 1 over y dx wedge dz. And as luck will have it, this is going to look a lot better in, this is going to look a lot better in cylindrical coordinates, but it'll look a lot better in spherical coordinates too. Okay, so what we need to do is replace this with phi inverse pullback of alpha. And this map is phi inverse, remember? Okay, so phi inverse pullback is determined by its differential, or its derivative, which is has 2 columns and 3 rows. So the first column is the derivative of each term in terms of phi. So this will be cosine phi cosine theta, cosine phi sine theta, and negative sine phi. Then the second column will be in terms of theta. So this will be negative sine phi, sine theta, sine phi, cosine theta, and then 0. Okay, so now we can compute what, for example, dy wedge dz and dx wedge dy are in many different ways. The way that I like to do it is I like to take, there's several different ways. You can plug in, sorry, we're not computing dy wedge dz, we're computing its pullback. The inverse pullback. Oh, right, and one more thing. I shouldn't really be talking about phi because phi is a terrible choice for parameterization because it's also a coordinate. So let's call this something else. Let's call it f. F. Okay. So there's a couple ways I can do this. I can compute it by plugging in, d by d phi and d by d theta and computing what that is. That'll be the coefficient in front of d phi d theta in the pullback of dy dz. But I personally like to just take the wedge product of the rows of df inverse. So this is going to be cosine phi sine theta d phi plus sine phi cosine theta d theta wedge negative sine phi d phi. And this is easy to compute because the only term that will survive is the wedge product of the theta and the phi. And I like to have my phi's first, so this is going to be sine squared phi cosine theta. Whoops, that's a theta. D phi wedge d theta. And similarly, f inverse pullback of dx wedge dz is the wedge product determined by these 2 rows. So the only terms that will show up will be the negative of the product of those 2 terms. So this will be minus sine squared phi sine theta d phi wedge d theta. And now I want to take the pullback of all of alpha. So I need to multiply this by 1 over x and multiply this by 1 over y. So this is going to be sine squared phi cosine theta divided by sine phi cosine theta minus, I'm subtracting, right, because alpha has a minus sign in it, negative sine squared phi sine theta over sine phi sine theta. And this is all the coefficient of d phi wedge d theta. Okay, so now let's just compute this. These are the exact same thing because everything cancels out. And so I end up getting 2 2 sine phi d phi wedge d theta. And so now my integral becomes the integral over sigma 2 of alpha is the integral. So I'm doing phi first. So theta goes from 0 to 2 pi. Phi goes from 0 to pi over 2 of 2 sine phi d theta. And this is something I can just compute fairly easily. So there's no thetas involved. So this is just going to be 2 pi times the integral from 0 to pi over 2. Oh, and I can also pull the of sine phi d phi. I can also pull the 2 out. So it's 4 pi times that. And then this integral is just 4 pi times, let's see, negative cosine of pi over 2, negative cosine of 0, which this is equal to 0, and this is 1. So I get 4 pi, which is exactly what Fortney gets in the book using a different parameterization.